My distinct pleasure and honor to introduce Aman Chadha. He's currently heading a team of generative AI scientists and managers at AWS Amazon. Previously, he was at Amazon Alexa team, Alexa smart speaker. And prior to Amazon, he was part of the machine intelligence neural design team at Apple, where he led a multimodal AI initiative for training on-device AI. And his research interests include NLP, computer vision, large language models, knowledge graphs, and all the top LLM ChatGPT variants, right? So before Apple, he was at Qualcomm and NVIDIA on ML accelerators and GPUs. So more not just about basic AI research, but also on-device AI, which is again, that's what billions of devices are used worldwide, right? So without further ado, I will leave the floor to Aman, and we're looking forward to your talk. Thank you.
Thank you so much, Surya. So let's get started, folks. Sorry for the difficulties, but we'll get started soon. So the topic for today's talk, as you guys can see, right? So we'll be going over generative AI. We'll cover a brief overview of the methods, the technologies that power a lot of the models that are currently in prevalent use, including ChatGPT and a variety of other LLMs and multimodal LLMs. So we'll go over some of that technology, and then we'll also cover some of the applications of these models in healthcare-related domains. All right. Yes. All right. So here's an outline of our talk today. So we'll get started talking about the past versus present picture of generative AI. How do these models look right now versus how they were before the ChatGPT wave back in December of 2022 set in? So we'll cover some of that overview. Then we'll go over the transformer model, the architecture powering a lot of these LLMs that are very popular right now. So we'll cover both the encoder side, decoder side, and also talk about encoder-decoder model architectures and what they're useful for. Now, this model was proposed back in 2017, the transformer model that set the wave of innovation in generative AI. So what I wanted to do after that was to also give you guys a brief picture of what has changed since then, right? What kind of innovations have we seen in the field that are powering a lot of these models that we have today. So that's going to be the LLM of today. And then we'll get into some biomedical or medical VLMs, LLMs, and VLMs are vision-language models, right? So more on the multimodal side. So we'll look at those as well. We'll start off with a quick overview of generative AI applications in medical domains. We'll go over some specific models that are very popular that have a biomedical flavor, MedPalm2 from Google, MediTron from EPFL. M3Health was actually a model that we trained in conjunction with IIT Patna in India. And then I have a list of some popular models beyond this as well that we won't be covering in detail, but should be pretty useful for some medical applications. And then we'll step into Agentic AI. Agents are quite the rage right now. So, this talk wouldn't be complete with an overview of agents and how they can help in medicine-related use cases. So we'll go over that as well. And lastly, we'll finish it off with an overview of the road ahead. What kind of techniques and research do we expect to see in this area? In the next 6 months to a year, what kind of trends can we predict and expect to see? So that's going to be the overview. And without further ado, let's get started with the status quo. Where are we today with generative AI, and where were we before the ChatGPT wave set in? So this slide is my attempt to give you guys an overview of some of the most popular architectures in generative AI. When people say generative AI, what do they exactly mean? So this is that overview. And what I've done is I've presented a then versus now view, past versus present view. So on the right, you'll see the past view. So you'll see GANs, variational autoencoders, flow-based models. Now, these models are pretty strong. They've been popular in their own times, but at this point, we've got a whole bunch of different models that are powering the wave of generative AI, which are the models on the left, right? So you'll see decoder-based transformer models, you'll see diffusion models. These are the two most popular classes of models model architectures that are powering the wave of generative AI innovation right now. So decoder-based transformer models, and we'll cover these in a lot more detail, but this is just an overview slide. And decoder-based transformer models are actually the architecture responsible for ChatGPT, for a lot of the Llama models, or most of the popular LLM, VLM names that you've heard of. So that is the single architecture powering a lot of these models. And like I said, we'll go into this in a lot more detail. But the other one's diffusion model, which is not going to be, it's outside the scope of this talk, but just to give you guys a quick overview, going from text to image, models, text to image, text to video models. A lot of those models are powered by diffusion models, where visual output is the primary motivation behind developing these models. So these models have two sets of processes: forward and reverse diffusion processes. Forward processes noise the image. They add noise to the image over various time steps, as you can see in the diagram there. And then the reverse diffusion process, which is what we use during inference to generate images or visual media, whether it's images or video, reverses the process going from noise to the image that is desired, right? Based on the textual input that you offer to the model, saying an image of a dog, jumping in the air to catch a frisbee, for example. So it's going to denoise the image accordingly at various time steps to get to the image that you desire. So those are diffusion models, but again, quick overview here, not the scope of this talk. We'll mostly be focused on transformer models, given that they are the ones powering the wave of generative AI that we have today. All right, with that overview done. So like I said, the next big step here is to look into what the transformer model is, what it's good at, what are some architectural variations that we see in the field when we talk about LLMs or transformers in particular. So what we have here on the left is actually a diagram from probably one of the most popular papers in AI right now, Attention is All You Need, published back in Europe in 2017. And this shows the original transformer model. This was back in 2017, right? So you'll see that the original transformer model went from inputs to, on the left, bottom left, to output probabilities on the top right, right? And when you try to break down what this diagram is telling you, right, you'll see that there is a component on the left, which I've highlighted in red. That particular part of the entire architecture is what is the encoder. And the encoder is great at coming up with embeddings for any input that you provide, right? And in this case, this model was used for the authors tested this on machine translation, going from one language to another, which is generally the task of going from one input sequence to another input sequence, right? So they plugged in inputs as your source language. The outputs on the right, bottom right, were the target language, and trained the entire architecture end to end, and out came output probabilities there at the top right, which were token by next token predictions going from the source language to the target language, right? But what we need to know here on the slide, the scope of this slide, is to focus on the part highlighted in red. That is the transformer encoder, the one that we use currently when we say BERT, or any of the variants of BERT. BioBERT, for example, is pretty popular in the biomedical side of things. And a lot of these variants are based on the encoder part of the transformer architecture. They do not utilize the part on the right, which we'll talk about as well, which is the decoder. But when we talk about ChatGPT and a whole bunch of LLMs that do generation, those are decoder-based models. So that's the part on the right and not the one on the left. But for the purpose of this slide, focusing on the part of the left, the encoder, as you feed in tokens at the input, bottom left, you will get at the output embeddings, which are semantic representations of the input. So that is the entire intent behind having a transformer encoder go from, input that you want to make sense of and encode semantically, and output are your embeddings or vectors, as they're popularly called, which are a semantic representation of the input, right? So the idea behind the transformer encoder was to design something that was supposed to be primarily used for input understanding. That was the entire goal behind this. The encoder wasn't used or intended for generative applications as such. But what this enables is a whole class of different applications because of the embeddings that it generates at the output, and we'll see some of that here. And the other thing I wanted to note here is that these models are trained a little differently compared to what decoder models or generative models are, trained with in terms of the objective or the loss that we use. These models utilize masked language modeling, where they're essentially predicting a token based on the tokens, surrounding that particular token. So based on context around a particular token, it's able to predict missing tokens. So it trains itself. So this is basically trained in a self-supervised way where you mask certain tokens and ask it to figure out what those masked tokens are based on tokens around it, right? So learning based on context is what these encoder models do. And we'll see a variant of that with decoder models as well. Self-supervised learning, again, is utilized for decoder models as well, as we'll see on the next slide. But these are primarily learned with masked language modeling, MLM as it's popularly called. Now, this is the how, right? Let's figure out the what and the why, right? What does this get us? Why train an encoder? Why use BERT? So the idea behind the encoder is that once you have embeddings for a particular input, you can look up similar, entities pretty easily by just measuring distance between embeddings, right? So these embeddings are pretty powerful. They are utilized in a whole variety of industrial domains, right from search recommender systems, just looking up similar items. Essentially the task of similarity search is what gets a big performance boost thanks to rich quality, high quality embeddings. So, the BERT architecture, that essentially was a transformer encoder. You could utilize it for question answering, for example. That's also possible with embeddings by just looking up, similar embeddings between a question and, an answer and a potential answer. So you can look at multiple different, say, options, say for a multiple choice question, gather embeddings for each of these different options and see which one has the best similarity with the question, right? So a lot of different ways to utilize embeddings, and what the original, the BERT paper that, popularized contextual embeddings did was it was trained on the book corpus. So it was trained on about 11,000 books with 3.2 billion tokens. And that's how these architectures got pretty popular. So this was the entire idea behind the transformer encoder, how it's trained, what it's useful for, and the part about similarity search using embeddings being the fuel for a lot of the systems that we have today, right from search to recommender systems to anything that requires us looking up similar items. All right. Any particular questions around this piece? We'll take questions live. I think we're also monitoring the chat, but anything that we can look at first before we head over to other. As we've got a packed agenda, we've got a lot of stuff to cover, but just want to take a moment to. Yes, please.
There are 700,000 tokens here beyond the words and punctuation.
Oh, okay. You're going from the words to the tokens?
Yeah.
So so 2.5 billion words are actually the same as 3.2 billion tokens. There's no delta here, or there's a 700K as a gap. And the reasoning here is that, just stepping back a bit, right? When you look at the input there in the diagram, right, the bottom left, the input there is not words, it's tokens. And each word is about 3/4 of a token. So in that sense, we split words using something called as a tokenizer, whose job is to figure out, parts, bits and pieces of every word that's fed into it, to figure out how we could semantically split it into various different constituent pieces, right? I think just a recording notification or. So, and this, by the way, the idea behind doing this is to make sure that when we have out of vocabulary words, or in other words, it's able to piece components of that word together and get a good idea of what this word means. So that splitting or chopping business that happens at the input, the tokenization process is what we call it. That is how it does that translation, going from 2.5 billion words to roughly about 3.2 billion words. But there are exactly the same in terms of input. There's no delta here, or no missing words or things chosen selectively. That's not the case. And all of these, that's a great question, by the way. All of these models operate on tokens and not words. That's a big part to emphasize. Whether it's ChatGPT or any form of LLM, everything is token based. So when it also, by the way, when it also does a prediction, as it's generating text, as you talk to ChatGPT and it's giving you text back, right, in response, it's generating things token by token. It's predicting the next token. It's not predicting the next word. So it takes in tokens at input, it predicts tokens at the output. So tokens are how these models interact with the external world. All right, we'll move over to the decoder. So like we talked earlier, right? So the part on the right is the decoder, and the decoder is actually the architecture that is essentially utilized, as you guys interact with any LLM out there, right? So whether it's ChatGPT or Claude by Anthropic or Llama or, all of these models are based on the decoder architecture at this point. And the decoder is essentially generative in nature. So it generates, like we discussed earlier, the output token by token. So it's sampling token one at a time. Which is why you actually see tokens coming in a streaming way on your ChatGPT screen, right, as it generates the output. So that's the entire idea behind, it's called autoregressive in nature. That autoregressive term essentially means that input at every time step is fed back into the model to generate output for the next time step, and so on and so forth in a sequential manner, right? So yeah, so the primary use case here, why do we have this? It's for text generation. Actually, that can be generalized to even images. It can generate tokens. Tokens could be text, it could be images too. So transformer decoders have been very commonly utilized for image generation as well, generating things pixel by pixel, for example, or patch by patch, as we like to call it. There are various levels of abstraction that these models can generate visual output at as well. But just for the purpose of this discussion, just sticking to text as the output modality, just like with ChatGPT, for example. So every token generated one step at a time, and it goes on auto-regressively. So that's what you see with these models. And the idea is that being fed in some input prompt where you ask, let's take ChatGPT as an example, a particular question, or give it some data and say, hey, I want to transform this data in a particular form, or I want you to write an email for me because I want to tell my boss that I'm out today, or so when you feed in that prompt, we call it the instruction that goes in at the bottom. The outputs that you actually see are the inputs to the model. In this case, once you slice the architecture and not utilize the part on the left, which is the encoder, and just restricting us to the part that's highlighted in red. So that's the input that goes in the prompt, and out comes token probabilities, where it chooses a particular token at any time step from a vocabulary of about anywhere from 50,000 to 250,000 tokens, depending on the model. So it makes that selection at every time step and starts generating response for you, one token at a time. So that is the idea behind the decoder, and this is probably the most popular architecture, like I said, that you'll see in generative AI right now. All of these LLMs, whether biomedical LLMs or general purpose LLMs, all of them at this point are powered by decoder-based models. And even on the multimodal side, like we discussed, right, whether it's generating images, that's also possible with decoder models, not just limited to the textual modality. So it's a pretty powerful architecture. Now, we looked at encoder and decoder, but how about so this is the original architecture, by the way, now the one with the encoder and decoder fused. This is how the authors of the paper, Transformer Paper, Attention is All You Need, proposed the architecture back in 2017. So it was the encoder and decoder fused together, where the encoder receives the input, generates embeddings, and these are then passed via the connection in between over to the decoder. Now, the idea at that point, which, there's a pretty different view right now in the field, and I'll talk more about that. But the idea at that point was to combine understanding of input and then generate output on the basis of that understanding, right? Hence, the generation of embeddings with the encoder, which get passed on to the decoder as a reference while it's generating the output token by token, right? So this was the original philosophy back in 2017, right, with the transformer paper. The idea was essentially, going from one input sequence to another, right? And like we discussed earlier, the task that the authors of this paper evaluated the model on was neural machine translation. NMT is what is popularly called, essentially translation, going from one language to another. I think they did English to German and vice versa, just to evaluate this particular architecture in the paper. But the idea was much more general than that, to be able to go from one sequence to another, right? So literally sequence transduction or sequence transformation is what they were after. Now, as we saw in the earlier slide with transformer decoder, the right part is what's powering a lot of the LLMs. So we aren't actually using the left part at all for ChatGPT and a whole bunch of these LLMs, which are good in a lot of cases, right? Where we've seen a lot of awesome things come out of these models. So the interesting development that happened in the field was you could just use the decoder and train it a little differently by just sticking in the inputs at the bottom right instead of the outputs where it says outputs here, and be able to train it to predict the next token. That's the only task these models were trained on, based on text that was already available, right, as ground truth. So we would set up input samples, the training samples, such that with given an input, we just hide the next token and ask it to predict the next token given a series of words or tokens at the input. And just train the model with backpropagation to make sure that its weights are aligned such that it predicts the right next token, right? So pass in feedback or using the loss function as the model's trained to make sure that the next token is predicted correctly. That's the only task, the objective that these models were trained on. And we saw great levels of performance, as you guys can see with a lot of these models in some use cases, especially day-to-day use cases. Niche use cases, there's still debate, and depending on what these models are good at versus bad at and the kind of training data that they've seen, there's obviously those caveats still. But we saw that the decoder architecture was pretty solid. So encoder-decoder is what we started off with, but at this point, the field has converged to a decoder architecture for mostly everything that's happening in the field, whether it's fundamental research or models in production, everything uses the decoder architecture.
I just have a question.
Yes, please.
Can dictionaries, particularly synonym dictionaries, play strong roles in the recognition of similarity at sentence level and decrease training documents required and get more interpretive accuracy? How is this quantitated and tuned?
Okay, I'll have some counter questions about this. Trying to understand, so dictionaries. So the way these models are trained is that internally, when you look into these blocks, and I wasn't planning to cover that as for this particular talk. There's a lot of blocks here, and what happens is these models develop an internal dictionary representation of the input in the form of a very huge hash table, where it's mapping inputs to the outputs and doing some form of approximate string matching. So when you feed it something that it has kind of seen at train time, it's going to be able to look up that internal hash table, which is the dictionary here, and come up with some form of output that is weighted across various different subparts of the input, right? So it mishmashes a lot of what it has seen across various different training corpora. So if it's looked at how to summarize research papers effectively, right? If it's been trained on some of that corpus, and then it's seen some PubMed data, right, which were just papers, right? No summarization. Now at runtime, at inference time, if you feed these models something that kind of interpolates between the two, something that's a middle ground between the two tasks that they were trained on, which is in this case would be, say, summarizing PubMed articles, right? It'll do a pretty good job at that, because stochastically what it's trying to do is trying to use the knowledge that it's gained from just summarizing research papers from, say, non-medical fields. It understands, based on that task, what the task of summarization is. And then when it knows that it's a PubMed article, so it's familiar with terms, on the medical side of things, it's able to put 2 and 2 together and give you a summary of your PubMed article, right? So internally, there are these dictionaries that are being formed. They're literally, the internal representations are queries and keys and values, and most dictionaries have keys and values. So this is, there is some form of information retrieval that's happening at an abstract level. You know, a lot of the explainability with these models is a bit of a challenge because these are huge models, and knowing why it output give you a certain thing at the output isn't easy. With traditional ML algorithms, it's way easier. But there's work being done. It's an active research field. But at a top level, this is how it's structured internally in terms of the internal dictionaries that it comes up with and matches, you know, the input to, you know, various different components that it's learned during training time. Does that give a what? Please?
So I was thinking like the whole point of attention is that you don't need to manually curate.
Correct.
Dictionary, right?
Yes.
Makes it so.
It makes its own, exactly. And which is why, you know, it's a fine balance there, right? So you do not have control over the specific dictionary entries that it's learning, right? Like you said, right? Manually, if you were to do it, you'll know what's going in. You can edit those entries, curate them. Can we do that here? There's work done, but it is a big challenge. It's definitely not a solved problem. In fact, even understanding those dictionaries is a challenge, let alone being able to modify entries so it prefers a certain response versus another, or in some cases, you know, with a lot of these companies, you know, having copyright issues, for example, with the training data that they use, can they remove certain entries? That's a field of active research, but that's absolutely a good point. Yeah. Any follow-up questions from Bruce?
I have one.
Yes, please.
Feel free to skip this if this is something that you'll be talking later, but you mentioned that the field has moved on to essentially using just decoder
Yes,
as opposed to more involved architecture.
correct. Yeah.
What encoder does, it provides this latent representation that
Yes.
embedding.
Yes.
So when you say that decoder is sufficient,
Yeah.
does it essentially imply that decoder in the process of training for the prediction of the next token
Yeah.
essentially creates its own
Yes, absolutely.
representation
Yeah.
that is just as good, if not better, than the encoder-based, the masking-based
Right.
embeddings?
Yes, that is absolutely correct. That is entirely the hypothesis we have right here, because the reality is that when you feed in anything at the input, it has to develop a latent representation that's good enough for it to understand what the input is to be able to generate the output, right? Without understanding a question that's posed to us, there's no way we can give a great answer, right? Unless it's just luck by chance, but go ahead.
As a follow-up,
Yes.
that what we call decoder is actually encoder-decoder.
Yeah, you can look at it like that. Yeah, absolutely. So these layers in between, right? What has happened is these models, and this is one of the big reasons why these models have grown in size, and now we need serious GPU hardware to be able to just run these models, let alone train them. Because what have people been doing is, if you look at the N number on the side, right, for both the encoder and the decoder, those are stacks of these layers, transformer layers. And people have been stacking them, you know, way more right now compared to how they were earlier with the encoder-decoder architecture. So essentially, we have way more decoder layers right now compared to, you know, the encoder-decoder architecture back when this was introduced. So we give the model enough degrees of freedom to be able to first synthesize a representation of the input that makes sense to the model, and then use that representation in later layers to synthesize an output, the next token that's, you know, most appropriate given the input. So absolutely, good question. Any other follow-up questions, Alison, on that? Okay, perfect. So let's move on to doing a time check. Oh, 11:30. Okay. So yes, what we saw up until now were, you know, the fundamentals, right? The basis of what makes generative AI happen today. So what I have here is a quick overview slide. There is a lot of detail in each of these areas, and I've linked a primer that I've written where each of these areas I've gone into in a lot of detail, explaining the motivation and how this helps and what these particular things are. But what I wanted to showcase as part of this slide, the intention was to show what has changed since the original transformer architecture. The architecture, interestingly, remains largely similar to what we had in 2017, even with the most recent models. It's the data piece that is where a lot of the magic lies when we see a lot of these new models, giving us output that, makes a lot of sense, a lot of use cases when they're being helpful for day-to-day tasks. It's a lot of the data that's at play. But the architecture has gone through some minor changes as well. I'll just summarize some of these very quickly. So the transformer architecture is based on something called a self-attention, where it weighs every input token as a weighted average of the tokens that surround that particular token, right? To understand things in context, right? How does one particular word affect the understanding of the other words around it, and vice versa? So that aspect is called self-attention. That is essentially at the heart of the transformer architecture. And what today's LLMs do, or even VLMs, multimodal LLMs, rather, they have we've optimized attention to the original attention at quadratic time complexity. So it would take n square, compute and memory to be able to generate an output token, because every token depends on every other token around it as part of the definition of self-attention. But there's been a lot of optimizations on the attention side. So you'll see flash attention, multi-query attention, group query attention. These are some of the optimizations that we have right now. GQ is actually pretty popular, whether it's Gemini from Google or Llama 3.1. A lot of these models now have moved on from the original self-attention to some of the more optimized versions of attention. Another key theme that we are seeing in a lot of these new architectures is the activation function. A lot of these models used to use ReLU as an activation function. I know this is a lot of technical terms, but I do have details there. And in the interest of time, I'm going to summarize these things real quick. But the ReLU activation function is probably the most common activation function you'll see in these architectures. And if you were to look at a diagram, of a transform architecture, you'll notice these activation functions here. And what we've done is there's been research in the field that has looked at improving these activation functions, and which, in turn have helped us train models faster. So there's faster convergence when these models are trained, and eventually that helps us train these models for even longer with more data, thereby leading to better performance, right? So there's been variants of these gated linear units that SWIGLU and GAGLU are the two most common ones right now that we see in Gemini, for example, use gated GLU. This is the next big change that we've noticed in some of these architectures. But largely the architecture remains the same. If you actually were to draw a block diagram of Gemini, or OpenAI does not reveal a lot of its architectural details now starting GPT-3, but we have a feeling it's pretty similar. Yeah, and there's some positional embedding changes as well. The original transformer architecture utilized something called as absolute position embedding, where every word that was fed into, every token that was fed into the model was basically encoded with a static, numbering, where, so for the model to know that this is word number 13 versus word number 11. Right now we have something a little more sophisticated than that embeds these positions relatively, so we don't have the model fixate on absolute position, because words could feature in various different ways depending on how the sentence is phrased. Even going from, say, active voice to passive voice, the order of words changes, but the meaning in some cases doesn't. So we made some of these improvements. Context length is the other one with Alibi, and where context length is essentially the amount of tokens that can be fed into the model at input. So there's been a lot of research here for these models to accept books and books at one go, entire huge code bases, videos, several hour-long videos. And you can ask the model to think, where was this particular scene where, say, the main character did blah or whatever. So it's able to mine through all of that data, all of those input tokens, and come up with an answer because of its huge context width. Gemini actually has a 10 million token context width right now. In research and production, I think it's 2 million still, but that's a lot of tokens. So yeah. All right. So yeah, quick overview of what's changed. Key themes are attention, activation function, context width. I'd say those are the three biggest ones. Go ahead.
So I know OpenAI does not reveal its architectural picture, but now since we have seen from the GPT-4 demonstration that it can do, it has very low latency. So if it's still doing automatic speech recognition, then text to speech, or does it have any optimization strategy which can convert speech to speech?
Yeah, that's a good question. So we do not know for sure because they don't make these details available. But there are open source models coming about that do the exact same thing. Obviously, at a level of performance that isn't quite right there with speech as yet in open source. But if there's one thing we've learned from closed source versus open source research is that open source takes a little while, especially in the AI world. This is a trend. Give it 3-4 months, 6 months, depending on how tough the problem statement is, and folks catch on to what's being offered out there in closed source. We've seen that time and again. Some of the initial architectures that we are seeing where they take in speech as input and are able to transcribe it, then feed that into the model for it to generate a response, and then do text-to-speech TTS back to generate a speech response. What they're doing is they're doing this inclusively within the model by actually feeding in these tokens directly rather than using an ASR automatic speech recognition layer at the input and a TTS layer text-to-speech layer at the output, right? And having a LLM sandwiched in between, right? That's the easiest way to actually develop a system like this. But that doesn't lead to real-time latency. So we've seen that, very frequently, because when you start plugging components together, disjoint components, right? Even though this would still work, but then it's not as the experience isn't quite there. There's, getting it done in real time is always a challenge. So what they're doing is they're feeding in natively these speech tokens at inputs and training the model to generate speech tokens at the output. So the model doesn't have to explicitly convert speech to text and vice versa at the output. And that is getting us some of the real-time latency. And one of the big things in this area, as far as speech is concerned, are state space models. There are a bunch of models that are coming out, and I'll talk about them at the very last slide. So those models are pretty good at low latency, and they are being used for speech more than these transform models now. We've only seen a couple of them come out, but there are big, huge benefits with those models, state space models, and maybe in the next 3-4 months, we'll see them taking over transformer models. So that is a big trend that we should be on the lookout for. Yes.
What architectural advances have gained performance for recognition and accuracy of negation and conditional multi-feature co-occurrence?
Yeah. So we have, this is an active research area, and with current ChatGPT models, for example, if you ask it problems or questions that involve anything from arithmetic reasoning to checking for mathematical properties like associativeness or transitive properties, you will see those models come up with interesting outputs that sometimes are way off than what is supposed to be the case. So that is where these models don't do well. And we have a whole bunch of augmentations to the transformer architecture for it to be able to look up with some internal database, which it again learns and is able to carry out offload a lot of these properties, and then and not get it done within the standard flow that we just saw earlier, right? The linear transformer flow, and then give you an answer back. Now, the easiest way to do something of this sort that we've seen in the field, and ChatGPT actually does this, is when you ask it a question where it thinks that it's best served with code, it actually generates the code and runs the code and gives you the answer rather than trying to do 2 + 13, because it knows it'll go wrong there. So they've trained the model in a way where it just offloads a lot of this to, writes Python code, runs a Python code with a code interpreter that it has access to. If it errors out during that process, it's able to go back and iteratively refine the code. So we'll get it to run over a couple of attempts in some cases if the problem statement is pretty complicated, but that's how it's adding numbers together and making sure that it doesn't give you something wrong. But in cases where it goes wrong and thinks that it can answer the question right, there was this example a couple of weeks ago. I remember reading 9.1 versus 9.9, which number is greater. It tried to answer it itself and it gives you the wrong answer. So if it doesn't think it needs to write code for something with reasoning, arithmetic, or other mathematical properties, we've seen it go haywire. So that's a big area of research to make these models natively get this right. Right now, it is offloading the configuration. All right. So next up, what we have are biomedical LLMs and multimodal LLMs, or VLMs, visual language models. So what I have here is this summary of, from this particular paper cited below that talks about various different domains where we're seeing, research, in the biomedical side of things, whether it's decision making, or the model to be an intermediate layer after receiving a set of symptoms from the patient. Can we come up with some hypothesis of what we think this is, which then gets served to the doctor for them to make a more concrete call, or to expedite their process, to streamline things for them, especially if there's a lot of patient load. So that is one key area where we're seeing a lot of the research happening in various different small pockets. Nothing that I've seen that's good to go and good to be widely deployed, but it's an active area of research. Clinical coding is another one, which is much more simpler, going from what the discharge summary of the patient was, mapping that to clinical codes. That's a relatively easier task for the model. So, in fact, it's a sequence to sequence task, what we looked at earlier, input sequence to output sequence, if you model it in that sense. So that's another area. Clinical report generation is pretty common too. That's where, medical professionals spend a lot of their time. So this is another area that a lot of startups and a lot of folks are trying to double down on to help reduce some of that load. Medical robotics, language translation. Language translation is pretty interesting because there's a lot of medical jargon and stuff that these models aren't great at unless they've seen a whole lot of medical corpora. And we'll look at some of that too in one of the coming slides. But that is an active area of research because it's way different from regular translation, which we call neural machine translation. That's just conversational language, and that's much more easier for these models to deal with. Medical education is another one, health support for therapy, for example, inquiry and response. So a lot of different pockets and areas where there's been a lot of work done, but of varying degrees. Each problem statement has its challenges. And depending on where there's flexibility for these models to, give outputs that might be suboptimal for in some cases where there's a human in the loop setup, for example, those models are receiving traction, but where there's no room for error, which is a lot of medical cases there, those are the biggest challenges for these models. All right, so we've got MedPalm M here. M is the multimodal variant of MedPalm. MedPalm actually has 3 different models, MedPalm 1, 2, and M now. And what this paper did, this was by Google, and you'll see on the right that given a image of an X-ray, it's able to come up with notes and its final analysis or diagnosis with the impression of what this particular case is. So the folks at Google came up with a multi-med benchmark. They put together a lot of data, working with doctors and professionals in the field to train this model across 14 different tasks. Came up with a model, trained a model at the end of the day, MedPalm M, which offered pretty good performance on some of these tasks. There were some gaps as well, obviously, that they're working on for the next iteration of this model, but out of the box, pretty good. And there was also some great zero-shot transfer that they saw where, like I discussed earlier, if you train the model on one particular task or a couple of different tasks, and then ask it something that involves an amalgamation of these tasks, something that fuses some of these tasks together, it's able to put 2 and 2 together and give you a reasonable response to some of these tasks. So they did see some of those emerging capabilities, is what we call it in the field. So emerging capabilities were seen. And performance in particular, they saw, this was the first, by the way, multimodal medical model by Google. All the prior MedPalm models were just text-based. So this was their first foray into giving the model, pictures of X-rays and whatnot and ultrasounds. And it's shown a good amount of improvement in report generation, for example, which is the example I have here on the slide. So that was MedPalm by Google. Oh yeah, if you're the data set mixture, right? Like I said, a lot of the magic with these models is in the data that they were trained. The architecture is still the transformer architecture with some variations here and there. So I wanted to dedicate a slide and talk about the data set. What are these models receiving as fuel to be able to generate some of these coherent responses, right? So they came up with USMLE style medical questions, medical entrance exam questions, all of these biotech professionals. A lot of this was put together, which is where a lot of the energy went for training a model like this. And on the right, I have something called as the data mixture ratio. This is a very common table that you'll see in a lot of the models that are trained. What this tells you is essentially, what proportion of the entire data set was, medical QA questions versus, say, medical queries or pharmacy-related questions, right? So having some of that pie chart structure, I think, is pretty essential to understand what the model focused on during training. So,
Question.
yeah, please, yes.
We have been told all the time that huge training sets, but these are minute. I mean, these are tens of thousands of data points, examples.
Yeah.
So can you elaborate on
Absolutely. That's a great question. So this is the fine-tuning data set. These models have been pre-trained on, so this is not what they start off with, but this is what they primarily focus on these are the skills they evaluate the model on later. In fact, these data sets themselves include components, test splits that we do not have that the model does not see during training, but is evaluated on later. But when we start off with these particular data components, we have a pre-trained model already that has seen enough of a corpus. Typically, it's PubMed, Central, abstracts and articles, and millions of those, and a lot more components put together. So the textbooks, for example, yeah, fairly common. I think I have some of that in a.
Authors of textbooks ever acknowledged?
That's a good question. Yeah. And the process that these companies follow is that they do have to consult and make sure that they go through the right channels. Whether Google did that or not, I'm not the best person to comment, but this should absolutely be part of the process, and I'm hoping that was done. PubMed Central, I do not think there are any scraping rules. A lot of the services recently, whether it's Stack Overflow or YouTube, there used to be a lot of these models trained on a lot of publicly available data, and now things are getting more challenging. Everything does go through layers of approval and stuff, or a lot of other services like Stack Overflow or YouTube, for example. I don't know what the latest there is for PubMed Central, but that forms a good, huge base and textbooks as well. And they do disclose a whole lot of these things. They usually do not specifically mention which textbooks and such these models were trained on. They do not make the data available publicly. These are public data sets, not the pre-training data sets as much. So, by the way, same with ChatGPT from OpenAI and a whole bunch of other models. Yes, time. How about Pankaj? We'll take your question later. Maybe I can connect with you after. I've got a whole lot of other sites. So MediTron, very similar focus as MedPalm. This was an LLM entirely, so there's no multimodal data. So this, by the way, talks about the pre-training process that we just discussed. So once you establish the corpus, there is the pre-training step, and then we do the fine-tuning on the data sets we just looked at on the prior slide for MedPalm 2. And the evaluation is typically on the fine-tuned data sets, the one we looked at. Pre-training is just to set up a generic base for the model to understand these terms and phrases and get a general understanding of things. Similar, data slide here for MediTron. So you'll see that, PubMed abstracts, papers, experience replays, general data that it's seen earlier, just to model language correctly, right? So Wikipedia, for example, is a very common one, just to pick up on language and how, linguistic details, how statements are formed, words and such. So clinical guidelines as well. So some of this is usually very common along with some textbooks just for pre-training. This was actually a model that we trained. This is in India's first open source multimodal medical LLM. And the focus here, the preprint isn't out yet, but the focus here was to have a model that could work with low resource languages where we did not have enough data. So we had to get creative and translate a whole lot of data that was available in English into these low resource languages using a different model, and then establish a pipeline to make sure that those translations were vetted for quality. So we just don't translate something and then send it over to train a model, because translation model itself could have issues. So that was the entire thesis behind pursuing some of this, but with a specific focus on Indian languages. So. this was the architecture of the model. That's the architectures on the left, right, are a set of queries that were translated in various different, Indian languages to English. And if you look at the architecture on the left, the key takeaway here is that we utilize a lot of a standard off-the-shelf encoder models. You'll see the text encoder, image encoder, Indic LLM. Those are frozen. So those were off-the-shelf models that are already available. But then we added a bunch of LoRa layers in between. LoRa layers are essentially used for fine-tuning in a parameter efficient way. So we don't fully fine-tune the model, but only fine-tune certain specific layers to make sure the process is efficient, because we were under a lot of compute constraints because this was done in a fully academic setting. So the fused both the input, the image and text input, and then ran an LLM on it to generate the output after translating a lot of the data that's on the right. Oh, yeah. So this is a list of general list of models that I personally interacted with on the biomedical side. There's LLMs, VLMs, there's embedders. Embedders are essentially the encoders that we looked at earlier. BioBert is very common, some of these models that I personally used, wanted to put those together on a slide. I think we'll make the slides available later, right? So we can share some of them. Just a general trajectory of what we have in biomedical LLMs and VLMs. We started off with BioBert, actually a pretty small model right now. Just came in a couple of years ago, and we've gotten pretty far. We have models several times that size, several thousands of times, maybe more. And there's bigger models coming. So if there's one takeaway here, it's that you'll need bigger and better GPUs to run a lot of these new models that are coming in. All right, Agentic AI. So I do want to cover some of this real quick, but agents are here to stay, and there's a whole lot of different use cases for agents, right? So I wanted to first give an overview of what agents are and what is the general philosophy behind agents, and then talk about agents in the domain of biomedicine. So anywhere we've got planning, we've got taking action based on some data. Agents are pretty useful. Reasoning, planning, and actions are the three most common use cases. So you'll see that you've got a brain in between. That's actually the model, the LLM, the main model, that is orchestrating a lot of this flow around it, right? So you'll see that on the left, it's got an environment where it's receiving data, which could be just us as users sending in prompts and input queries to the model. Then it goes to a perception stage where it tries to make sense of that. It could be various different forms of input data, could be text files, papers in PDF form, images, videos, sensor data. All of that is perceived, and outcome embeddings, those dots that you see are the embeddings or the internal vectors that we discussed earlier, that the model, the latent representation that the model comes up with. And then the LLM, the brain in between, figures out if it needs to use its internal memory, external memory, anything that it needs to look up from the web and retrieve to be able to come up with some plan of how it wants to serve your particular input query. And next step where it needs to take action is where agents get involved, right? So if, say, we want the model to call an external tool and be able to carry out something, a desired task, we could have an agent there which interacts with the external tool, calls an API, or invokes the external tool in various different ways and takes action, right, based on what you require. So the action part is central here, and that's where agents are key. A lot of the other areas you could still use the same LLM or VLM to carry out reasoning, planning, perception, but taking action does require setting up an agent, right, on the basis of what it's perceived from your input. So that is the heart of what an agent is. And what I have here are a couple of slides that give you a walkthrough of how agentic AI is being used in biomedicine. And again, this is in very early nascent stages right now. So we don't have a whole lot of work done, but there's papers coming in every now and then. This is a very active research area. For example, this use case right here is essentially, it's trying to simulate an AI hospital where there's, the doctor, receiving symptoms from the patient, and there's a chief physician who's looking to train the doctor by monitoring what the output of the doctor is and then giving it feedback based on what the chief physician thought would be a great diagnosis based on particular symptoms versus what the doctor saw, right? And in that sense, it forms that loop where the physician and the chief physician are just interacting with each other, and there's training happening in this environment. So this was one particular framework that just came out pretty recently. I've linked the paper. But again, like I said, in pretty early stages, we aren't taking any action or anything as yet with a lot of these frameworks. We're trying to see how to best model some of these setups in a biomedical setting and seeing what's possible. This was another paper that came out, I think, last month or so, and this was focused on education as well, where you had the agent that was initialized with a lot of the information about the particular patient, the symptoms, the exams and tests, so it could receive, reports, and any X-rays or radiology reports. All of that could be consumed directly, and based on prior medical reports as well, all of that put together, it would come up with a hypothesis or a particular diagnosis, and then you could have it go through a practice session with another agent in a multi-turn setting. So you could, it could ask questions, get feedback, refine it, and then go back and forth. So the multi-turn setting was pretty important here, and that was the focus behind this work. All right. So that brings me to one of my last slides here. I think, oh yeah, this is the last slide. So we spoke about a whole bunch of different things today, right? And I alluded to state space models earlier. So that's the first thing on my list here. These models are catching up pretty quickly. They are superseding transformers in a whole bunch of different ways. They have linear time complexity, first of all, with transformers, like we discussed earlier. The way the internals work and the definition of attention that powers transformers is based on quadratic complexity, but what these models are inherently linear, so they are way quicker, like we discussed earlier with speech or real-time use cases, where you don't have the luxury to wait for a couple of minutes before any response. These models are pretty good at that. And they also have infinite context length, which is also a big blessing here. So you can feed it a lot of data, and it can churn through that data, make correlations across modalities, and give you a response based on, putting a lot of this together. So those are state-space models. Hallucination is a big problem with some of the models that we have right now. And there's a lot of research done here. I've, worked on a bunch of papers here as well. And being able to detect hallucination and then subsequently mitigate it is a very active area of research. And there's a lot of work happening, but there's varied levels of success depending on the input. There's no one size fits all at this point. So this remains one of the biggest challenges we have with these models. And if you do not have enough guardrails around some of these models, there's a lot that can go wrong. So it's important to make sure we responsibly deploy them. Causal reasoning and attribution is another big area. It's very difficult for these models to derive causal relationships. They're very good at correlations and not as much causal relations. But there are some specific architectures that have come up, which again augment the current transformer architecture or come up with something way different, but they have their limitations. The transformer architecture got popular for a reason. It's very good at what it does, stochastically figuring out the next token. So doing something, putting something together from scratch, already puts you at a little bit of a disadvantage, even though it's good at, say, deriving causal relationships. Omni few shot learning is basically, right now, the models that we have right now go through a lot of data to come up with a performance level that's acceptable, right? We need enough data in all kinds of different domains and across different demographics. If it's a medical data, that's pretty challenging to have in a lot of cases. So being able to teach these models tricks without having them learn from reams and reams of data and having just access to limited data in low resource scenarios is a big area of research, where give it few examples and the models are good at coming up with a reasonable response. So that's one thing that's being worked on. Missing modality is another. What if you have one particular modality associated with the patient, but you do not have something else, but the model at train time had seen, say, X-rays along with textual content or reports? It's not going to do as much of a good job because it expects multiple modalities then at runtime. So being able to come up with models that can tackle missing modalities is another area. And lastly, like I discussed earlier, agents, especially for mission critical applications like healthcare, where there's very little leeway to go wrong. We do not quite have the technology and agents at a stage right now where they're able to take action and, in some cases, irreversible action, right? So we do need humans in the loop at this point, and but the technology is, coming together pretty fast, as you guys have seen. It's just a year and a half since we had ChatGPT, and we're already at much bigger and better models. So we're getting there one step at a time. So yeah, these are some of the key themes and areas for what we expect to see in the near future with GenAI. All right, that brings me to the end of my talk. Thank you.
But I will open the floor for a few more questions.
Yes.
Ask many questions. I promise my last one.
Please.
Neural networks are very finicky and hard to predict. We don't know which architecture is going to work.
Yeah.
We don't know how to train given the architecture.
Yeah.
So how is this progressing so quickly? Is it just sheer number of people trying many different things, or is there something else going on?
Yeah, so there is some empirical science, like you said, sheer number of people trying things. That is part of the picture because it is there is intuition though in the field. So it's not like it's a total random guess, but it is very difficult to predict with, especially if you have a brand new problem statement with a modality that, very few have dealt with, right? So if you come up with a new sensor, that, you get data from now for patients, which model architecture do we use that would, do well for a use case like this? There's intuition that, folks like us rely on as we train these models. We understand what works well, what doesn't. There is very little out there that is, written up or, disclosed in a lot of these things. And the companies do it intentionally in some cases because those are trade secrets at the end of the day. So this is a short answer to a long, there's a long variant as well that I have, but there is some intuition. But at the end of the day, some of these models are called foundation models for a reason, because you can feed them a whole lot of data and with some intelligent techniques, have them do a whole lot of things. Unless it's a problem statement that is just radically different from what they can ever conceive, which is usually not the case, right? So, trying out stuff empirically with some of these models, using them as a foundation and trying to build something on top is usually a great idea, because problem statements do have some correlations with what the model's seen usually. So that's what, a whole lot of people start off with.
Great talk, by the way.
Thank you so much.
Any other questions?
Yes, go ahead.
Microsoft recently came up with this model 3.5 vision.
Yeah.
So, and we see that it is a 3.8 billion parameter model based
Yeah.
on 5D mini.
Yeah.
But we see that based on their benchmarks, this model is performing better than GPT-4o for visual question answering. And GPT-4o is a much larger model,
Yeah.
even though it's a distilled version of GPT-4.
Right.
So does it have something to do with the scaling laws, or, do you have any thoughts about that?
Yeah, scaling laws for sure. That is one big part of the picture, because what a lot of companies go for is to ensure that the models that we train, and by the way, anything that goes through training, especially pre-training for a lot of these big tech companies, it requires a whole lot of money. Pre-training models is very expensive compared to just fine-tuning models. So the idea is that we could be a little lax with our scaling laws and train bigger models, and in fact use the same models later to fine tune them with even more data over time, right? And thereby come up with, say, GPT 4.5 from GPT 4, right? By using those same checkpoints because they're already bigger models, and then acquiring more data over time, and then showing these models additional data, and then coming up with a new checkpoint, right? So there's that incremental approach, which is why these models are trained a little bigger than what they should have. So scaling laws are what determine, what size of model would be appropriate given, say an X number of tokens. And what we do is we usually tend to put in some margins there. The other thing with 3.5 is there were some reports of them doing very well on certain benchmarks, but then Later on, there were also reports of them having trained on test data sets. And once you do that, then the models get very good at offering performance. But at the same time, that's not something that's ethical because you don't know how the model will generalize in the real world. The test data sets are meant to give you an idea of how the model would perform. So they're not supposed to be trained on. But there was some, research done that actually led to a lot of papers after this was observed to understand how we can predict if a certain model had seen the test data while it was being trained. And it might not, by the way, not be intentional. A lot of this data is available on the web, and as folks scrape the web for pre-training data, for example, or even fine-tuning data, some of that data gets it's part of the pipeline, and it's difficult to extract unless you know for sure that it's being added unconsciously or unintentionally. Yeah.
One final question. Sorry. Last question, please.
Yes.
How far is AI singularity? I'm just curious because everybody claims like something.
Yeah, and there's you'll see a whole lot of companies focusing on AGI now and trying to in some ways we are there, in some ways we are not there. And a classic example of that would be the mathematical reasoning that we spoke about earlier, right? If you make the model compare two numbers that look and sound similar but are not similar, it's not able to figure out which one's greater versus which one isn't, right? So I think that's a very classic example of these models for there to be room for improvement for these models, right? Because until we can get those fundamentals right, I think it's difficult for there to be AGI or singularity. So in that sense, there are fundamental problem statements that we need to chase first. A whole lot of other day-to-day general use cases, ChatGPT is actually pretty good at, right? And I personally use it all the time. It's very beneficial, does simplify things. But I do think the fundamentals, a lot of these things have to first be taken care of. And the funny thing is the tasks that appear very simple to us are the most challenging to AI, and in most cases, the other way around as well. This is, like I said, a poster child example, a canonical example. So until we fix things of this sort, I don't think we're going to get there anytime soon. Yeah.
So whenever you see all these models, they are trained with like billions of tokens and
Yeah, trillions right now, actually. Yeah.
Like a human being doesn't like maybe reads 11,000
Yeah,
through a
correct.
lifetime.
Yeah, they're not efficient. Yes.
Where are these models lagging and what
Yeah.
can we do?
Yeah, in some ways, that's not a big problem as well, because if you think about it, these models are also better than you and me on a lot of tasks, right? So if they've seen more data and then that lets them be better at certain tasks, that's not a bad thing, right? So it's intentional in those cases. But the reality is that the training process that we have right now, which by the way hasn't gone through any major changes in quite a while, several years, that I think also requires an overhaul in terms of how we train models and how we make the process effective. If you look at a 2 or 3 year old, they might have only seen, they visually absorb a lot of data. And if you look, there's been comparisons done where you look at the amount of pixels they've seen over the span of 2 or 3 years versus the kind of tokens these models have seen. And these models are several orders of magnitude. They've consumed much more data than what kids have. And, but if you then extrapolate the same thing to say a 20 or 30-year-old who's good at what they do in their specific field, it still doesn't hold. These models still have consumed a lot more data. So there are definitely training process efficiency improvements along with architectural improvements like state space and stuff. All of that put together is, I think, going to be the next big wave of Gen AI.
We'll follow up with the training meeting. Thank you.
Thank you so much for taking the time.